So, welcome you back. In the last few lectures, what we have done is the Fourier transform, Fourier sine transform, Fourier cosine transform of functions, the properties of different Fourier transform, properties of Fourier transform, Fourier sine transform, Fourier cosine transform, that we have done. And also we have done the Fourier transform of derivative of a function or integration of a function. Afterwards, we have done the convolution theorem, we have done the Parseval's identity, and we have also seen using Fourier transform how to evaluate an integral. So, all these things already we have covered. In this particular lecture, what we are going to do, we will try to solve some problems, so that you will be acquainted with the system, that how to find out the Fourier transform of various functions or how to evaluate the integrals using the Fourier transform. That thing we will do here. So, let us take one example over here first. Find the Fourier transform of e power minus x by x. To find out the solution, Fourier, your function is f of x is equals to e power minus a x by x. Now, what is Fourier sine transform, which we are denoting as capital F of s of alpha. This is equals from definition, as you remember, root over 2 by pi 0 to infinity f x into sine alpha x dx, where your f x is e power minus x by e power minus a x by x over here into sine of alpha x dx. So, from definition, Fourier sine transform of alpha equals root over 2 by pi 0 to infinity e power minus a x by x into sine of alpha x dx. So, effectively I have to evaluate now this integral 0 to infinity e power minus a x by x into sine of alpha x dx. Let us assume that I equals this integral, that is your, or you can assume that I can assume this 0 I is this one sine of alpha x dx. To evaluate this integral, effectively what I can do, I can use the normal integration approaches, or the last example, if you remember what we have done, we have made the derivative of the given integral, means we use the differentiation under the integral sign, we obtain d d alpha, then we obtain d2i d alpha square, and we form one ordinary differential equation, and using the ordinary differential equation we are finding the solution of that ODE in the form of CF plus PI, where in the complementary function was consisting of two arbitrary constants and whose value also we evaluated in the same fashion. So, we will use the same similar approach for this particular problem also. First, what we will do, we will try to find out the derivative of this integral, and then we will see how we can solve this thing. So, d d alpha of this f s alpha, d d alpha of this f s alpha, that is from here I am finding the making differentiation with respect to alpha on the both side of the given equation. So, that it becomes root over 2 by pi 0 to infinity. This x will be cancelled, sin alpha x is there. So, this x will come out, x sin alpha x, that will be cancelled, you will obtain e power minus a x into cos of alpha x dx. And this using normal integration approach by parts, I can integrate this thing. Once I am integrating this, you will obtain the value as e power minus a x by a square plus alpha square into minus a cos of alpha x plus b plus alpha sin of alpha x, and the range of x is from 0 to infinity. This I am not showing directly, because in this case what you are obtaining, d ds of f s alpha equals this integral and e power minus a x cos of alpha x. this integral is a standard integral. So, directly we have written the result. So, that once you are putting the limiting value of this, you will obtain a by a square plus alpha square will come here, and this root over 2 by pi will come over here, and for all other values will be 0. So, what you are obtaining d d alpha of f s alpha equals nothing but a by a square plus alpha square into root over 2 by pi. So, I am rewriting this thing again, that is d d alpha of f s alpha, this is equals to root over 2 by pi a by a square plus alpha square. Once I obtain this, from here again f s alpha I can tell, that is f s alpha will be a is constant root over 2 by pi, simply it is d alpha by a square plus alpha square, plus some constant of integration will come. So, here you see, once I am integrating, once I am differentiating with respect to alpha, I am getting this function d d alpha of f s is a common function of a by a square plus alpha square. So, that now integrating on the both side, I can obtain the value, and this particular integral is very known integral, the integration of d alpha by a square plus alpha square. So, this we will obtain root over 2 by pi into this a will be cancelled, and tan inverse alpha by a, one actually the value of the integral is nothing but 1 by a tan inverse alpha by a. So, since I know the value of this integral very easily, so I am just a will be cancelled, so that you will obtain root over 2 by pi tan inverse alpha by a plus c. So, now you have to do what? You have to now find out the value of c only. To find out the value of c, what you will do, when alpha 0, what is f s alpha? I have to find out. Your f s alpha, if you remember, f s alpha equals, you have written root over 2 by pi 0 to infinity e power minus a x by x into sin of alpha x dx. Since your f s alpha is this, so whenever alpha is 0, therefore, you will obtain f s alpha, this is equals, since alpha is 0, sin 0 is 0, so that you will obtain f s alpha equals 0. This implies, if you put the value of this f s alpha equals 0 for alpha equals 0, this tan inverse part also will vanish, and so that you can obtain c equals 0. Therefore, your Fourier sine transform of the given function equals, you can write down root over 2 by pi tan inverse alpha by a. So, please note this thing, that without using any other normal techniques, we are just differentiating once I am differentiating this, and then I am getting an integral whose value is well known to us, and directly I am using the value. And after that, to evaluate the value of the arbitrary constant c, you are using for alpha equals 0, what is the value of f s alpha? From the integral, I am finding f s alpha is 0, so that it implies c equals 0. Therefore, your result is this one. So, let us see once this thing. So, Fourier transform of this one was there. So, I am just writing from the definition, Fourier sine transform of alpha is this. Now, differentiate both sides with respect to alpha, then left hand side will be d d alpha of f s alpha, which is equals root over 2 by pi into this integral. And if I evaluate the integral, I know the standard result, e power minus a x by alpha square plus a square into minus a cos of alpha x plus alpha sin of alpha x, where the limit of x is from 0 to infinity. If you substitute it, you will obtain d d alpha of f s alpha as nothing but a by a square plus alpha square into root over 2 by pi. So, that f s alpha, Fourier sine transform of the given function, can be written in terms of integral. The value of the integral is 1 by a tan inverse alpha by a, and a will be cancelled, plus a constant c will be arbitrary constant c will be added. So, whenever alpha is 0, Fourier sine transform of alpha is 0. So, that value of c arbitrary constant is 0. Therefore, you are obtaining Fourier sine transform of alpha equals root over 2 by pi tan inverse alpha by a. So, various techniques are available, as you are seeing, by observation, by checking what kind of problem you are trying to solve, what kind of result you are getting. You have to decide actually what actual technique should be used, so that without pain, with much difficulty or in much easier way, I can solve the problem. So, let us take the next problem, that is, find the Fourier sine and cosine transform of 2 e to the power minus 5x plus 5 e to the power minus 2x, although the function looks like very easy. So, first one is, we will find out Fourier cosine transform of the function 2 e power minus 5x plus 5 e power minus twice x. This equals, always using the linearity property, you can write it as 2 into Fourier cosine transform of e power minus 5x plus 5 into Fourier cosine transform of e power minus 2x. This again, you see, the use of the properties, using linearity property, I can break it down just like we have done it for the case of linear transform also. We are breaking this into two parts, and then we will solve this one. Now, this Fourier cosine transform of e power minus 5x, this equals, from the definition, 2 into root over 2 by pi 0 to infinity e power minus 5x into cos of alpha x dx, plus similarly 5 into root over 2 by pi 0 to infinity e power minus twice x into cos of alpha x dx. So, effectively, now you have a formula, you have an integral basically of the form e power minus a x into cos of b x dx. Both are of this form. So, I have to evaluate only this integral 0 to infinity e power minus a x cos b x dx. And if you remember, already we have done these problems, and this is again as a standard result. The result is a by a square plus b square. So, please note that 0 to infinity e power minus a x cos b x dx, this is equals a by a square plus b square. So, if I substitute this result over here, so this actually we are using this result to obtain this thing 2 into root over 2 by pi into, then a is here 5. So, that 5 by 5 square plus alpha square, and for the second part similarly 5 into root over 2 by pi. Here your a is 2. So, that it will be 2 by 2 square plus alpha square. So, once I am getting this, you see, now here I have used simply a standard result of this integral, and I am obtaining the result very easily. So, if I simplify this particular result, you will obtain 10 into root over 2 by pi into 1 by alpha square plus 25 plus 1 by alpha square plus 4. So, although my integral was little difficult, but the way I have done it using the standard results of integration, I am just substituting this value using this result, that 0 to infinity e power minus a x cos b x dx, this is equals to a by a square plus b square. I am getting the result very easily over here. So, once you can see it from here now, first I am finding out the Fourier cosine transform of this using linearity property I am breaking it. Then I am using this property that 0 to infinity e power minus a x cos b x dx, this is equals a by a square plus b square, and I can obtain the final result like this. Now, let us take the next problem, that is we have obtained the Fourier cosine transform of this function twice e power minus 5 x plus 5 e power minus twice x. Let us find out the Fourier sine transform of this function now, that is the second function. I think now it is understandable to you. So, Fourier sine transform of 2 e power minus 5 x plus 5 e power minus twice x, this is equals to, again on the same way using linearity property you can write it 2 into Fourier sine transform of e power minus 5 x plus 5 into Fourier sine transform of e power minus twice x. So, that this equals, you can write down 2 into root over 2 by pi into 0 to infinity e power minus 5 x into sine of alpha x dx, and this part will be 5 into root over 2 by pi 0 to infinity e power minus 5 x, sorry not minus 5 x, but this will be e power minus twice x is here. So, minus twice x into sine of alpha x dx. So, effectively similar integral here also is coming, which we have to evaluate. What is the similar integral? Similar integral is 0 to infinity e power minus a x into sine b x dx, and the value of this one is b by a square plus b square. So, again I have to remember that the value of this standard integral 0 to infinity e power minus a x sine b x dx, this is equals b by a square plus b square. So, if I use this result, then I will obtain as 2 into root over 2 by pi into alpha by 5 square plus alpha square plus 5 into root over 2 by pi into alpha by, here your b is 2. So, 2 square plus alpha square. So, that if you just simplify it, you will obtain alpha root over 2 by pi into, here b is alpha, please note that in the result it was b by a square plus b square, and b is your alpha here. So, I am getting here alpha by 5 square plus alpha square, and here alpha by 2 square plus alpha square. So, by taking alpha common, this will be 2 by alpha square plus 25 plus 5 divided by alpha square plus 4. So, we are obtaining this result. So, Fourier sine transform of twice e power minus 5 x plus 5 e power minus twice x is this result. Let us see this thing. So, you are obtaining here Fourier sine transform is this equals, I have written directly this thing, where we are using the value of the integral as 0 to infinity e power minus a x sin b x dx equals b by a square plus b square. You will get this result, and if you simplify, you will obtain the result as this one. Next, see, find the Fourier transform of Dirac delta function delta t. If you remember, Dirac delta function already we have defined when we have used the Laplace transform. When we were studying the Laplace transform, Dirac delta function was defined, and fully we defined it, and then we find out what is the Laplace transform of a Dirac delta function. Now, let us see how to find out or what is the Fourier transform of the Dirac delta function. So, you know this thing, Dirac delta function is defined like this. This is equals 1 by epsilon, where t lies between 1 to a to a plus epsilon. A very large force is effectively acting for a very small period. If you recall it, the value is 0 otherwise. So, the Dirac delta function is defined like this. The delta epsilon t minus a equals 1 by epsilon whenever t lies between a to a plus epsilon and 0 otherwise. So, that as epsilon approaches 0, this value will approach always infinity and it will make an infinite rectangular strip basically, or which we have told a large force is acting for a very short period. Now, let us see what would be the Fourier transform of this one. If you recall, just I am writing a to b f x dx, this equals, you can write down this thing where epsilon lies between a to b. So, that this xi lies between a to b and this is nothing but the MVT, that is mean value theorem. From the mean value theorem, you can write down this thing. So, if I use this mean value theorem of integral calculus, then you can write down by integrating on both sides of the Dirac delta function t minus a into dt. This is equals 1 by epsilon into a to a plus epsilon f t dt. So, this is equals effectively I am writing it 1 by epsilon a to a plus epsilon a t f t into dt, and this using the mean value theorem I can write down 1 by epsilon a plus epsilon minus a into say f of some other function eta, where your eta lies between a to a plus epsilon. So, ultimately this epsilon would be cancelled and you are obtaining the value as a less than eta less than a plus this thing. I am sorry, I have missed one thing, that is here into f t will come here, this into f t will come here, because otherwise f t will not come here, or in other sense in Dirac delta function first you are multiplying on both sides of the given equation by f t and then integrating from minus infinity to infinity. So, that this actually is nothing but minus infinity to infinity delta epsilon t minus a into f t dt. This term is this one, and this is equals 1 by epsilon actually minus infinity to infinity f t dt, but the value of this function is such that in a to a plus epsilon it is 1 by epsilon, for all other interval it is 0. So, that directly we have written 1 by epsilon a to a plus epsilon f t dt. Now, using this mean value theorem this we can write down 1 by epsilon into a plus epsilon minus a into f eta, where eta lies between a to epsilon. So, that you are obtaining the result as f eta. So, therefore, your minus infinity to infinity delta epsilon t minus a into f t dt, this is equals f eta. Now, as epsilon approaches 0, means because what will happen, this will be minus epsilon to epsilon delta t minus epsilon. So, it will be delta t minus a into f t dt, whereas there you had f eta, where your eta was lying between a to a plus epsilon. So, whenever epsilon approaches 0, eta will approach a. So, that you are obtain f of a. So, please note that as epsilon approaches 0, minus infinity to infinity delta t minus a f t dt, this is equals f of a. Now, come to the our original problem, that is Fourier transform of delta t minus a. So, please note that till now only I evaluated this thing. I have shown that minus infinity to infinity delta t minus a f t dt, this is equals f a. Now, Fourier transform of delta t minus a, this is equals 1 by root pi minus infinity to infinity e power I alpha t into delta t minus a dt. from the definition of Fourier transform, we can write down this thing, and this is nothing but from using this particular one. What is this? Minus infinity to infinity delta t minus a f t dt is f a. Here your f t is e power I alpha t. So that you will obtain this value equals 1 by root over pi into e power I alpha a only. In this case, here it is f a and your f t is e power I alpha t. So, now you can understand why we have shown initially this thing. Therefore, the Fourier transform of delta t minus a is equals to, the Dirac delta function equals 1 by root 2 pi e power I alpha a, and Fourier transform of delta t, that is when a equals 0, then simply it will be equals to 1 by root over 2 by pi. So, Fourier transform of Dirac delta function delta t equals 1 by root 2 pi. This equals, you can write down 1 equals root over 2 pi into Fourier transform of Dirac delta function. This you can write down, or if I take inverse Fourier transform, then if inverse Fourier transform of 1, this is equals root over 2 by pi into delta t. From here you can write down this thing. If I take inverse Fourier transform on both sides, then root over 2 by pi delta t, this equals, you will obtain Fourier inverse this, or in other sense you can write down that delta t equals 1 by root over 2 by pi into Fourier inverse of 1, or again from here you can write down root over 2 by pi into delta t. This is nothing but then from minus infinity to infinity 1 into me e power minus I alpha x into d alpha. So, what we have obtained is the Fourier transform of delta t minus a is 1 by root 2 pi e power I alpha a. Whenever you will make a equals 0, Fourier transform of delta t equals 1 by root pi. And also we are showing that minus infinity to infinity e power minus I alpha x d alpha, this is nothing but root over 2 by pi into Dirac delta function, that is delta t. So, let us see it quickly. From here, once we are getting this, we know what we have proved initially. So, Dirac delta function we are defining as 1 by epsilon whenever t lies between a to epsilon, otherwise 0. Then you are integrating, you are multiplying by f t on both sides and integrating from minus infinity to infinity. And now, this second term I am obtaining using the mean value theorem. So, that the value I am getting f eta, as epsilon approaches 0, you will obtain this one minus infinity to infinity delta t minus f t dt is nothing but f a. Now, I am finding the Fourier transform of delta t minus a, and using the earlier result I can tell the value is e power I alpha a by root over 2 by pi. Similarly, if I put a equals 0, then I will obtain Fourier transform of delta t equals 1 by root 2 pi.